Hello everyone and welcome back to this video. For today we will solve this set of 8 exercises where we will try to solve a different kind of direct integral techniques, where we will see how to discover which kind or which rule to apply to solve the different kind of integrals. We will begin with the I exercise, which is an integral of x d of x over square root of x squared plus 1 all these power 3. I equal to integral of x d of x over square root of x squared plus 1 power 3 d of x. Okay, for now it's possible, we can see that it's possible to rewrite this square root has x squared plus 1 power 3 over 2, and we again have in the numerator x d of x. On the other hand, we can see that the derivative of this argument x squared plus 1 must be the derivative of this argument is very similar to the denominator that we have here. This is the derivative of x squared plus 1, it's equal to 2x d of x, so that here we can write x d of x has d of x squared plus 1 over 2. If we substitute this expression by this, we have I now equal to 1 over 2 integral of d of x squared plus 1 over x squared plus 1 power 3 over 2. And this is the same thing as 1 over 2 integral of x squared plus 1 power minus 3 over 2 d of x squared plus 1. For now, we can see that if you look at or watch the previous videos, this looks like has integral one of the rule that we started previously, which is integral of f power p d of f equals 1 over p plus 1 f p plus 1 plus c, where here we can see that f for us is equal to x squared plus 1 and our p is equal to minus 3 over 2. Then we can apply this rule to solve this exercise, where from here we can see we have that I will be equal to 1 over 2. I will write here again, it's x squared plus 1 power 3 over 2 d of x squared plus 1. Then applying this rule, we get now it's equal to 1 over 2 times 1 over minus 3 over 2 plus 1 times x squared plus 1 power minus 3 over 2 plus 1 plus c. And now we have here, we must write 2. We simplify 2 by 2 and we get I will solve this step by step. Okay, here we have 2 and we get 1 over 2 times 1 over minus 3 plus 2 over 2. Then we can simplify 2 by 2. Here x squared plus 1 minus 3, if we put 2 here, no, 2 over 2 plus c, and we have minus 3 plus 2 is equal to minus 1, and then we get minus x squared plus 1, and here we have minus 3, this minus is here only power 4 to 3. We have minus 3 plus 2 is equal to minus 1. Then we have minus 1 over 2 plus c has the solution for this integral problem. Here, where this one. I will show you that this is actually the solution for our problem, where we are considering that this is our solution, which is the f, capital F, and we must take its derivative, which is minus 1 over 2 times x squared plus 1 power minus 1 over 2 minus 1 times 2x, and this is equal to minus by minus is plus, then we have 1 over 2 x squared plus 1. If we put 2 there, we have minus 1 plus 2 over 2 times 2x, and now we must simplify 2 by 2, and we get x power, we have x here time x squared plus 1 power minus 3 over 2, which is the same thing written as x over x squared plus 1 power 3 over 2, and it's actually the same thing written as x over square root of x squared plus 1 power 3, which is our little f, as we can see here in our exercise, this one. It's okay for this exercise. We will continue solving the exercise B, which is B. Exercise B is I equal to cos of 2x over sine of 2x d of x. To solve this exercise, From here, we can see, we must remember, for example, we must remember that the derivative of sine of 2x is equal to 2 cos of 2x d of x, so that we can write cos of 2x d of x has 1 over 2 d of sine of 2x, and we can substitute this expression by this in our integral, so that now we have I equal to integral of cos of 2x d of x over sine of 2x equal to 1 over 2 d of sine of 2x over sine of 2x. Then, and from here, we can apply the following rule. We must apply the following rule. Again, I advise you to watch the previous video to remember these techniques. We have the following rule. Integral of d of f over f is equal to ln of f plus c. Then here we can see that our f function is equal to sine of 2x, so that we have now I has equal to 1 over ln of sine of 2x plus c. If you apply the same rule as we applied in the previous exercise, we can see that if this is our f, then the derivative of this function must be equal to this, must be equal to cos of 2x over sine of 2x. Here also we can see that cos of 2x over sine of 2x it's equal actually to the inverse of the tan of 2x, which is cot of 2x. Then here we are saying that the integral of cotan of 2x must be equal to ln, so must be equal to 1 over 2 ln of sine of 2x. Then okay, for this exercise it's okay, we will continue solving the next exercise, which is the c. It's equal to 1 over x. Okay, c, it's I equal to 1 over x ln of 2 over x d of x. For solving this exercise, we must remember one of the logarithmic properties, which tells us that log of x, a function f, over a function g, is equal to log of log with the base a, for example a here, f minus log with the base a of g. We must remember these properties of logarithms. And from here, we can see then we can write as an integral of 1 over x over of ln of 2 over x d of x has equal to integral of 1 over x ln of 2 minus ln of x d of x, so that it's equal to ln of 2, which is a constant. This then we can take out from the integral, and we have for the first term only d of x over x minus integral of ln of x over x d of x. Here we can see that we have for the first, I will call this as I1, and I will call this as I2. For I1, I have only the integral of d of x over x, and to solve this part we must remember the following rule. Integral of d of f over f is equal to ln of f plus c. For now, we will only include the constant of integration for the I, the full I. This is actually the same rule that we applied for the previous exercise, which is this one. And now this means that I1 is equal to ln of x. On the other hand, here we have for I2 it's equal to integral of ln of x over x d of x, which is the same thing, ln of x times d of x over x. If we remember the derivative of a logarithmic function, ln function, this is d of x over x. This means that we will substitute this expression by this one, and we can solve this is I2. Then I2 it's equal to ln of x d of x over x, it's equal to integral of ln of x d of ln of x. And to solve this integral, we must remember the other previous rule we used for the first exercise of this video, which is integral, here we have this rule, integral of f power p d of f is equal to 1 over p plus 1 f plus time p over power p plus 1, where then from here we can see that our f function is equal to ln of x, and our p is equal to 1, which is the potential of, or the exponent of ln, which is 1 for this exercise. And then I2 will be equal to 1 over 2 ln square of x, and the constant of integration we will include for the full I. And for now we have then we have I as equal to ln of 2 times I1 minus minus ln, okay, minus I2. minus I2 plus the c, the constant of integration. And we have then it's equal to ln of 2 times I1, which is ln of x. Okay, this is ln of 2 times ln of x minus 1 over 2 ln square of x plus c. This is the solution for our integral problem. Okay, we can write these using the property of logarithms but for now we will only stop here. This is the solution, and we can take the derivative of this solution to show that actually this is the solution for this exercise. We will continue solving the problems D, which is D where U, D is arctan of 4x. Okay. We have for D, I equal to integral of arctan of 4x over 1 plus 16 x squared d of x. Here, to solve this exercise, we must remember that the derivative of arctan of a function f it's equal to 1, or it's equal to d of x, d of f over 1 plus f squared. And from here we can see that if we applying this rule, and from here we can see that if we choose f has 4x, yes, then we are saying that the derivative, let me change the color of the pencil, and we can see that the derivative of arctan of 4x it's actually equal to v of 4x over 1 plus 4x squared, which is equal to 4d of x over 1 plus 16x squared. Then for now we can write d of x over 1 plus 16x squared has 1 over 4 derivative of arctan of 4x. And now we will substitute this expression in our integral by this one here, so that I, which is equal to integral of arctan of 4x over 1 plus 16x squared d of x, we can rewrite as 1 over 4 integral of d of arctan, this is equal to 1 over 4 integral of arctan of 4x times d of arctan of 4x. And here we can see that we must apply the rule. Integral of f power p d of f equal to 1 over p plus 1 power p plus 1 plus c, where here our f function, this is the rule, and for our exercise our f function is arctan of 4x, and our p is equal to 1, which is the actually exponent of the arctan. Okay, now we see that our I will be equal to 1 over 4 arctan of 4x d of arctan of 4x is equal to 1 over 4 times 1 over 2 times arctan of, or arctan square of 4x plus c, and this is 1 over 8 arctan square of x of 4x plus c. Then also here, if we define this as our fx, we can take the derivative to show that this derivative will be equal to the original function that we have in our exercise here. Okay, we will continue solving the exercise E. The exercise E, which is 5x power 3. Okay, here we have, for the exercise E, I equal to integral of 5x power 3 d of x over 1 plus 16 x power 4. Here, to solve this exercise, we can see that the derivative of a function, firstly, we can take out 5 because it's a constant, and write our integral has 5 times integral of x power 3 d of x over 1 plus 16 x power 4. And we can see that if we have a function of a constant alpha plus a constant beta time x4, if we have this as a function g, for example, of x, the derivative of a function g, it's actually equal to the derivative of the function alpha plus beta x power 4, which is equal to 4 power times beta times d of x power 3 d of x, so that then we can stop here for this example. This means that here we can see that we have this x power 3d of x, which is actually the same thing that we have in our numerator for our exercise. And we can choose beta and alpha for different numbers. But if alpha is equal to 1 and beta is equal to 16, then we can see that we will have the denominator function for our g of x, so that it's more simple to transform our numerator as our denominator and get a direct integral. How can we do this? We are saying for now that we can write x squared, or no, we can take the derivative of 1 plus 16x power 4 as our function f, and take its derivative as 16 power times 4 times x power 3 d of x. And here 16 times 4 is equal to, we have 24 here, and we have, okay, it's equal to 64 times x power 3 d of x, so that x power 3 d of x can be written as 1 over 64 d of 1 plus 16 x power 4, and we can substitute the x power 3 d of x with this expression in our integral here, and we have now I has equal to 5 times 1 over 64 integral of d of 1 plus 16 x power 3 power 4 over 1 plus 16 x power 4. And again here we can see that this integral has the function as d of f over f, which is equal to ln of f plus c, and this is plus, and we can take our solution written as 5 over 64 times ln of 1 plus 16 times 4 power 4, 16 power x power 4 plus c as our solution. If we take the derivative of this expression, we must get the original problem, which is this one. And from here it's possible to see, if we take the derivative of the ln, it's equal to 1 over its argument, and the derivative of this argument will be equal to 16 times 4 times x 14 for 4 power 4 3 power 3, and we simplify 64 by 64, and we get the solution as we have in the original problem. Okay, this is the exercise E. Then we go to the exercise F, which is where you exercise F. Okay, it's x. Okay, Okay, exercise f is I equal to x d of x over 1 square root of 1 minus x power 4. And here we can see that x power 4 can be written as x square, where then we can take the derivative of x squared, which is equal to x d of x, and here we have that x d of x is equal to 1 over 2 d of x squared. Okay, and now we can rewrite I as equal to integral of the x d of x over 1 minus x square, and this is where we have x d of x. We will substitute with this expression so that we have 1 over 2 integral of d of x squared over 1 minus x square. Okay, from here now we must remember that integral of d of f over square root of 1 minus f squared it's equal to arc sine of f plus c. And for our exercise, our f function it's equal to x squared, and we can apply this rule to get the solution written as I equal to 1 over integral of d of x squared over square root of 1 minus x squared, and the solution is 1 over 2 arc sine of x squared plus c. Okay, we solve this exercise and we will solve the G exercise, where G exercise. Okay, G exercise is Euler power ton. Okay, the exercise G is I equal to integral of tan of x over cos square of x d of x. Is this one? Yes, isn't this? Okay, what can we do with this exercise? For this exercise, we can take two paths to solve. With the first one, remember that the derivative of tan of x is equal to d of x over cos square of x. Then from here we can rewrite our integral I equal to Euler power tan of x over cos square of x d of x as integral of Euler tan power tan of x d of tan of x. And from here, using the following rule, integral of a power f d of f is equal to a power f over ln of I of a plus c. So that here for our exercise, our f is equal to tan of x and our a is equal to e. So that now I equal to integral of e power tan of x d of tan of x, it's equal to Euler power tan of x over ln of e plus c, and we know that ln of e is equal to 1. Then our solution is equal to e power tan of x plus c. This is the solution. On the other hand, we can observe that the derivative, we can observe that the second path for this case, we must see if we have, I will write here with the other color, if we have I equal to integral of e power tan of x over cos square of x d of x, we can observe that the derivative, the differential of Euler power tan of x, it's actually equal to Euler power tan of x over cos square of x d of x, so that we can substitute in our integral this term by this one, and we have I equal to d of Euler power tan of x, and from here, using the following rule, integral of f d of f is equal to f plus c, and from here we see that I must be equal to Euler power tan of x plus c, as we observed for the other procedure. Okay, now we will solve the last exercise for this video, where to remember here, we are applying different kind of rules of techniques of integrations to solve different kind of integrals, and we are learning different techniques to transform. We are learning, or we are trained to use techniques of transformation to get a specific fashion of integral and use the rule for this kind of integral. Then we will solve now the last exercise, which is the 8th exercise. Okay, sine of log of x. Okay, h is I equal to integral of sine of ln of x over 2x d of x. Okay, for now we can see that 2 is a constant, then we can put take out from the integral, and we get 1/2 integral of sine of ln of x d of x over x. On the other hand, we can remember here that the differential of ln of x is equal to d of x over x, which means that where we have d over x, we can substitute by this expression, and we have I has equal to 1/2 integral of sine of ln of x d of ln of x. And we must use here the following rule: integral of sine of f d of f is equal to minus cos of f plus c, where our f function for our exercise is ln of x, and we have now I equal to 1/2 minus 1/2 cos of ln of x plus c has the solution. Thank you for watching this video, and I am asking you to put like on this, share with your friend, and subscribe in our channel for more videos of the same kind of this one. Thank you. See you in the next video.